Hello James, welcome back to another video. The grind for BITSAT 2022 is on, and today we are discussing the frequently asked BITSAT questions from the chapter of work, energy, power. Those are new to this channel, do check out the older videos of this series. I don't have much to say, let's get to the video. So let's briefly go through the topic weightage for this chapter in BITSAT over the last 15 years. Okay, so first let me tell you that work, energy, power is an important topic for your BITSAT. Okay, so you can at least expect 3 to 4 questions from this chapter straight in your BITSAT paper. Also, all the previous topics that we have discussed from units and dimensions to this chapter are very important. Okay, so do check them out if you haven't already. The further topics will also be important. I'll tell you when the topics are important and when they are not. Okay, anyways, let's go through the weightage for this chapter. Let's go through the topic weightage. Okay, and let's see which topic has higher weightage in this chapter. Okay, so our topic number 1 is work done. Okay, you can see that only 2 questions were asked in the last 15 years of consideration. Okay, so 2 questions from this topic. Okay, and these questions were majorly formula based. They asked you to use work done equals F dot D. Okay, so yeah, formula based questions from this topic. Now coming to our topic number 2 is conservative and non-conservative forces. Okay, not that important topic. Also you have the relation between conservative force and potential energy. So on that, one question was asked. Okay, so our next topic is kinetic and potential energy. Now this is an important topic. You can see that 5 questions were asked in the last 15 years. Okay, so here the questions are more favored on potential energy. Okay, and that too on spring. Okay, so you are supposed to know that the potential energy stored in the spring will be given as half kx square, right? That formula is very important. So the potential energy in spring itself is a very important topic for BITSAT. Okay, so also kinetic energy, you'll know it as half mv square. Okay, so formula based questions from this topic. Okay, and 5 questions, right? Now coming to our next topic, which is my favorite topic from this chapter, work energy theorem. Okay, and sadly no questions from that topic, but anyways we'll practice one in today's class because I'm biased. I love this topic. Okay, anyways, let's come to our next topic, that is types of equilibrium. Okay, now in this chapter you learn about the 3 types of equilibrium, right? The stable, unstable, and which one is that, neutral. Okay, so those 3 types of equilibrium. On that, one question was asked, I think on potential energy or something. We'll come to that in a while. Now next thing is power. Power is the rate of doing work, right? So yeah, on that also one question was asked. This question was purely formula based. I think they had asked you to use power is Fv, right? F dot V. Yeah, that relation. Yes. Now coming to our next topic, again conservation of energy. Now I thought this would have heavy weightage in BITSAT, but sadly it does not have. Okay, it is a very simple topic, but only one question was asked from this topic. Okay, so I think just yeah, only simple application of conservation of energy. Initial mechanical energy equals final mechanical energy, and I think solve for velocity or something like that. Okay, solve for unknown basically. Now coming to our next topic, which is now our important topic. Okay, important topic from BITSAT point of view. You can see that 6 questions were asked from collisions. Okay, so collisions is an important topic for BITSAT, and the split is mostly in favor of your inelastic collisions. Okay, so I think the ratio will be 1:2. Okay, no questions were asked on oblique collisions. I think 1:2 ratio is there between elastic and inelastic collisions. Okay, so inelastic collisions are more favored in BITSAT. Okay, so inelastic collisions is something you should focus on. Okay, now our next topic is conservation of angular momentum, the most important topic from this chapter. Okay, you can see that 7 questions, literally 7 questions were asked from this topic straight in your BITSAT paper over the last 15 years. Okay, so half the time in the last 15 years the questions were asked from conservation of momentum. Okay, so again simple topic, and you also use conservation of momentum in collisions, right? So yeah, this topics can be mixed up with one another. Okay, so skipping any one of them is a bad idea. Okay, Now the next topic is coefficient of restitution. Not that important topic. This is something that you learn in collisions. Its value is 0, between 0 and 1, or 1. Okay, so yeah, that is basically you learn it in collisions, right? It's the ratio of velocity of separation to velocity of approach and things like that, but it's not important. No questions asked on that. Okay, you might be asked questions on the value of E for a particular type of collision. Okay, so that becomes a theoretical question. Suppose if I ask you for this question is likely to come. Okay, so that is why I'm saying it. So what is the coefficient of restitution for perfectly inelastic collision? So that is 0, right? Because there is no separation between when there is inelastic collision. So question like that. I think one question was asked from this topic. I'm not very sure. So yeah, that not that important topic, but yeah, let's come to our next topic. Okay. So next topic is chain systems. Again, this is a subset of potential energy. I would say this is a particular type of questions. Chain systems is a chain problems, right? Those you might have seen in your book. So one question was asked on this chain problem. So majorly it's based on potential energy. Okay. So majorly you should focus on conceptual part of this chapter. You should also learn the formulas properly, and you should also focus on theory. Okay, just like the coefficient of restitution value for your different type of collisions. Okay, so that is theory, formula, F dot D, other formulas, and concepts. Okay, of course, concepts are what needed everywhere in physics, right? So I think that is all what I have to say about the weightage. Let's dive into a lot of questions now. So coming to topic number 1, work done, right? So let's dive straight into the questions. Question number 1, here you are given the force in vector format. The displacement is also given in the vector format. You are supposed to tell what is the work done. Okay, very, very simple question. What will you use? You'll use the work done is given as F dot D, right? Here you are just supposed to take the dot product of this two, right? And that will give you your answer. In dot product, you just multiplies the i's together, the j's together, and the k's together, and add them all, right? So 5 2s are 10, right? 3 and minus 1 minus 3, 3 1s are 3 and minus sign, right? And 2 into 0, right? So that is 0. So 10 minus 3, that is 7 joules, right? Or whatever the unit may be over here. So 7 is the correct choice over here. Option B, 7 is the correct choice over here. Okay, so just simple dot product over here and you have your answer. Okay, now second one is a bit tricky. Okay, you can see that the mass of this object is given and the VT graph of this object is given. Okay, mass of this object is 10 kg and the corresponding VT graph of this object is given. Okay, this object is performing some motion and its VT graph is over here, velocity versus time. Okay, you can see that initially when time is 0, the velocity is 50, right? Velocity is on the y-axis, and when the time is 10 seconds, the velocity is 0, right? The y value becomes 0, which means velocity is 0 when time equals 10 seconds. Okay, here you are supposed to tell what is the work done in 2 seconds. Okay, so first of all, again we'll use the same thing. What is work? Work is basically force into displacement, right? So force into displacement, that is the thing we are going to use over here. Okay, and from VT graph we can find the acceleration, right? So force, we can write it as mass into acceleration, right? So mass we have, acceleration we'll find from this. Okay, we can find acceleration as it will be the slope of this graph, right? So you can find acceleration by, if you see the change in velocity, right? Change in velocity is minus 50, right? Final velocity is 0, initial is 50. So final 0 minus 50 and divided by the time taken for this is 10 seconds, right? So your acceleration is minus 5 meters per second square, right? Acceleration, you can see the slope is negative, so the acceleration should be negative, right? So you have your acceleration with you, you have your mass, you are just supposed to find what is the displacement in 2 seconds. Okay, so once you find the displacement in 2 seconds, substitute it over here, substitute all the others values, and then you'll get what is the work done over here. Okay, so let's find the displacement. So displacement will use S is equal to ut plus half at square. Okay, you can see that the initial velocity is 50 when time is 0. The velocity is 50 into t, so that is 2 plus half a, acceleration is -5, so a into t square. We are supposed to find displacement in 2 seconds, right? Because we want to find work done in 2 seconds, for which we need displacement in 2 seconds. Okay, so 2 seconds over here. Okay, time is 2 seconds over here. 2 and 2 cancels. Here 50 2s are 100, minus 5 2s are 10, that will be 90. So displacement is 90. Substitute the values over here. Mass is 10 kg, acceleration is -5, and displacement is 90. Okay, so 9 5 is 45, 40, 450. So 450 into 10 minus 4500, right? 4500 joules. So option C, minus 4500 joules is the correct choice over here. Okay, we just wrote work equals force into the displacement, and here if you see force, we have written it as mass into acceleration. Acceleration we found out from this graph, right? Change in velocity by the time taken, and we found out the displacement using this S is equal to ut plus half at square, since acceleration is constant, right? So that is all from work done. Let's move to our next topic. So our topic number 2 over here. Now I have brought a lot of topics together. You can see conservative force, kinetic energy, potential energy, equilibrium, power, and energy conservation. Okay, so these are the topics that we are going to discuss over here, because I brought them together because they have very low weightage, right? So yeah, that is what we are going to discuss. We are going to discuss one question per each maybe. Okay, and you'll see more questions from this topic later in composition. Okay, in mixed with some other concept. Okay, but for now let's solve the straightforward questions from this topic. Okay, so question number 1 over here you are given a spring. I told you springs are favored, right? So yeah, they are the privileged ones. So K value of a spring is given over here. The initial extension of that spring from the natural length, okay, it's initially extended a length of 5 centimeters. What will be the work done if you extend from 5 centimeters to 15 centimeters? Okay, what is the work done in this process when you take it from 5 centimeters from its natural length to 15 centimeters from its natural length? Okay, so this is a process over here. You are supposed to tell what is the work done. Now work done in such type of cases is basically given as the change in potential energy or negative change in potential energy. Okay, so you are just supposed to find the difference in the potential energies in these two configurations. Okay, so one potential energy u1, suppose u2. Okay, potential energy over here u1, potential energy over here u2. u1 minus u2 gives you the potential energy or the work done in the process from here to here. Okay, so that is the basic idea over here. We'll just use work done as change in potential energy. Okay, this is valid for conservative forces, right? Potential energy itself is defined for conservative forces, right? So potential energy, final potential energy, that will be half k x square, right? In terms of spring, it is half k x square, where x is the length from this natural length, right? And length, the extended length measured from the natural length. Okay, so I'll write x2 for now. This is the final length, if you see, and here k x1, the spring constant does not change, of course, so you can take half and k common, so x2 square. Now if you see in final configuration, the x2, the extension is 15 centimeters, and that square, 15 squared, is 225 minus, if you see in the initial configuration, x1 square, right? So 5 square, that will be 25. Now each of this is in centimeters. In order to convert it into meters, you'll multiply 10 to the power minus 2. No, 10 to the power minus 4. It is squared, right? So yeah. So here let's substitute the values. Half into k value is 800. This is, how much is this? 200. and 10 to the power minus 4. You'll see 4 zeros over here, 1, 2, 3, 4. This goes with this. 8, 2 and 2 can go, right? And 8 will be left. So 8 joules. Option B, 8 joules is the correct choice over here. Okay, I hope the approach is very straightforward, right? You just find the difference in the potential energy into configurations and that will be your work done. Okay, now coming to question number 2, here you are given a spring force as a function of x, okay, as a function of that extension. So you are supposed to tell what will be the work done in stretching it L length, okay, L length from the natural length. Okay, so how will you do this? You are given the force, you know something from here, right? That work done will be basically the change in potential energy. Now there is one more formula which says that conservative force, now spring force is also one of the conservative force, it's given as del u by del x, okay, where u is the potential energy. This is the relation that we are going to use, and we'll integrate this. Once you integrate the potential energy du, when you integrate this, you'll get the change del u, right? You'll get this del u, and del u is nothing but work done, right? So that is our basic idea. So I'll just write it in this way. So now let's integrate it. So integrate it from where to where? We'll integrate it from 0 to the length L, right? We want to find the work done in carrying the string from 0 to L. Initial is not given, means that it is at the string is not extended. Okay, it's basically it's not stretched. Okay, so initially the length is 0 and then you extend it to length L. Okay, so yeah. So let's put the value of f over here, and 0 to L will integrate it ax square plus bx into del x. So just integrate it with respect to x, and here you'll just find u1 to u2, right? Or we can write delta u for this. Okay, so delta u, and here let's integrate it. So a is a constant, a and b are constant, it was given in the question. So x square integration of that is I think I've made a mistake over here. Yes, there is a mistake in this question. It is ax and bx square. Okay, so this was the question. Okay, so let's modify that over here, ax plus bx square. Okay, so when you integrate x with respect to this, you'll get x square by 2, right? Now we are supposed to apply the limits, plus here when you integrate, b is a constant, it comes out, and integration of x square, that is x cube by 3. Okay, and you are supposed to apply the limits now, 0 to L, right? This is the difference in potential energy, and which is nothing but the work done, right? So here you'll get it as a L square by 2 plus, when you apply the limits, upper limit minus lower limit, right? Lower limit is 0, so no use of substituting 0 over here. So yeah, just substitute the upper limits. Here you'll have b L cube by 3. Okay, so a L cube by 2 plus b L cube by 3. Option C is the correct choice over here. Okay, so you just use this relation. Okay, integrate it. I hope you know how to integrate, or else check my video on integration. Okay, so simple integration over here. Substitute the limits, get your answer. That simple. Okay, so let's move to next set of questions in this topic only. Okay, we have more questions to discuss from this topic. Okay, so let's go to them now. So question number 3 and 4 over here. In question number 3, you can see a ball of mass 20 kg on a hill which is at a height of 100 meter from this line, okay, from this reference line, and then we have another hill which is at a height of 30 meters. Okay, this ball is basically beginning with an initial velocity of 0. Okay, initial velocity is 0, and then it rolls down this hill, and then finally it comes down to this flat ground. Okay, this flat ground is also at a height of 20 meters from the reference that we have chosen. So here you are supposed to tell what is the velocity of this ball when it is just dropped from this hill. Okay, it begins initially with initial velocity 0. Okay, its mass is 20 kgs, and rest of the data also you have. Okay, so what is the velocity of the ball when it reaches the flat ground over here? Okay, it is given that these hills are smooth, there is no friction over there. Okay, So here we can use our classic conservation of energy, right? So you can write initial mechanical energy is equal to final mechanical energy. Okay, so if you see, initially the ball begins at initial velocity 0, so no kinetic energy, only potential energy, right? So which is given as mgh. So I'll write that mg into h. Okay, so this is the initial energy. Finally, okay, won't see this intermediate thing, we'll just move from here to here, right? So yeah, so finally if you see, the ball is moving with a velocity some v, okay, which we have to find. So half mv square, this is the kinetic energy. Does it have potential energy? It's a flat ground, come on, it should be 0. No, it is not 0. Okay, if you see, it is at a height of 20 meters. Okay, so there is some height, so there will be some potential energy. Okay, we measured height from this reference line, right? So mgh. Okay, now this height is 20 meters. Okay, so I'll use capital H over here for 100 meters, and this is small h, 20 meters. Okay, so it's still above the reference line, right? So there is some potential energy to the ball. Okay, so now mgh. Now for m here, we can cancel this m throughout, right? Cancel this throughout. Now just substitute the values. G is 10, and this is what? H is 100, so 1000. Okay, half into v square. V square is something which we will find, v is something which we will find. G is, again, we'll take it as 10, and h in this case over here is 20, right? So here 200 minus 1000 is 800. 800 into 2, right? 800 into 2 will give you v square. V square is nothing but under root of 1600, which is nothing but 40, right? 16 root is 4, so 1600 root is 40. So option B, 40 meters per second, is the correct choice over here. Again, this approach is very long. You could have just used V equals under root 2gh, right? So result from kinematics, or an object comes down by height h, then its velocity should be under root 2gh. Okay, so if you see over here, if you substitute 2g, g is 10, right? And h, if you see, h is nothing but 100 minus 20, right? It comes down a height of 100 minus 20, this height, right? So this is 80, right? So this is 800 into 2, 1600, again 40. So this was the shorthand approach of doing it. Anyways, 40 meters per second is the correct choice over here. Okay, now let's come to our next question. Here you are given potential energy of a system as a function of x. Okay, is given over here. Okay, a and b are constant. And here you are defined with a term d. Okay, you are supposed to find this d term at equilibrium. Okay, what is the value of this d at equilibrium? Okay, it is given that this d value is equal to the minus of the potential energy at equilibrium. Okay, so first of all, you have to find the potential energy at equilibrium, right? And then make it negative, and that will be your d value, right? So what is the equilibrium point? First of all, how will you find the point of equilibrium? Okay, so in order to find potential energy at equilibrium, you should know this value of x at equilibrium, right? So basically, what is equilibrium? Equilibrium is a condition wherein the net force on an object is 0, right? Or you can define it one more way, in terms of potential energy, that del u by del x. Okay, the differentiation of potential with respect to x is 0, also with respect to y, also with respect to z. Okay, so basically the differentiation of potential should be 0 with respect to x. Here in this case will be 0. Okay, this is the condition for equilibrium. Okay, basically if you see, if you can remember it from question 2, I think that was question 2, I don't know. Okay, somewhere we discussed that the force is del u by del x, right? And the conservative force is del u by del x, right? And I told you that equilibrium is a condition where the net force is 0, so this essentially becomes 0, right? So that is what I'm saying is the condition for equilibrium. Okay, yeah. So now what will you do? You'll just find the derivative of this and equate it to 0. Okay, and that will give you your x at equilibrium. Okay, so you'll find the position at which the equilibrium occurs. Okay, and that x you'll substitute in this equation and you'll get the answer. I know it sounds too much. First, let's differentiate this. Okay, so once you differentiate this, on the left hand side you get this term. Okay, on the right hand side you'll get a, okay, minus 12a upon x to the power 30. Okay, I'm just taking this x to the power 13 on top and I'm applying the n minus rule. Okay, so basically if you have x to the power n, the differentiation is nx n minus 1, right? So that rule I'm applying over here. Okay, and here you'll have minus 6, so that will become plus 6b upon x to the power 7. Okay, now you have to equate this to 0, right? You know that this term is 0 over here, so once you equate it to 0, what will you get? You'll get the position of x at equilibrium, right? You will get a value of x for equilibrium to occur. Okay, so 12a upon x to the power 13 equals 6b upon x to the power 7. Okay, so 6 2s are, so 2a is equal to 2a by b is equal to x to the power 6, right? We are cancelling x is not equal to 0, of course. Now we have found the position at which the equilibrium occurs. We have found the position x where the equilibrium is established. So let's substitute this x over here and we'll find the potential energy at equilibrium. Okay, so that is the basic idea. Okay, so let's substitute it over here. Okay, so we'll substitute x to the power 6 as 2a by b. Okay, so here potential energy at equilibrium, or we'll say potential energy at equilibrium, right, is a upon, now x to the power 12 just means x to the power 6 square, right? So x to the power 6, we know it as 2a by b, and that is squared, right? X to the power 6 squared. Okay, minus b upon x to the power 6, which is 2a by b, right? So here you'll get, what will you get? ab square upon 4 a square minus b square upon 2a. This a and a will get cancelled and you'll have b square upon a, I can take that common, so 1/4 minus half, or I can take 2 as well common, so 2 is common, so half minus 1. Okay, so just basic calculations, so minus half, so minus b square by 4a. Okay, so minus b square by 4a is the potential energy at equilibrium, but you are supposed to find d, which is the negative of the potential energy, which will be plus b square by 4a. Okay, so option C plus b square by 4a is the correct choice over here. Okay, so you just write this condition for equilibrium, then you then you differentiate this equation, equate it to 0, because that from there you'll find the position of equilibrium. So once you find the position of equilibrium, substitute it over here, find the potential energy at equilibrium, and then d value will be minus of that value, right? So that is how you do this question. Let's go to the next set of questions now. Only one question left from this topic. Here we have to use conservation of momentum and little bit of energy conservation. Okay, so in this question you can see a block of mass m moving with a velocity v. Okay, this is a spring of spring constant k. Okay, when this block moves and hits the spring, okay, when there is collision between the two, the length compressed by this block, okay, due to its momentum is L. Okay, now this block will go and hit the spring, right, and it will compress some length. Okay, that compressed length is L. Okay, you are supposed to tell what is the momentum after collision. Okay, what is the momentum after collision if the compressed length is L. Actually, momentum will be conserved. Momentum is in fact conserved in all type of collisions. Okay, so a final momentum will be also mv. Okay, so initial momentum is equal to final momentum. Okay, so basically it will be mv, but if you see over here, they want the answer in terms of k and l, right? K and l. Okay, so what they are asking you to do is apply energy conservation. Okay, there is no frictional force involved over here, so you can write the initial energy, initial mechanical energy is equal to the final energy, right? So initially the energy is in the block, okay, it's kinetic energy half mv square, right? Finally the energy is in the spring when you compress the entire length of the spring, okay, not entire, this length L, okay, so half, that energy is half k L square, okay, the compressed length half k into L square, right? So this half and half will get cancelled. You are just supposed to find a relation between V and k and L. Okay, so that is the idea over here. So V square you can write it as k by m into L square, right? And then V you can write it as under root km into L, right? So this is the formula for V. Now we know that initial momentum is equal to final momentum, so we can just find this momentum, initial momentum, which is mass into velocity, and that will be equal to the final momentum or momentum after collision, right? So mass into velocity, so mass is m, velocity is this, so which is under root k by m into L, right? So this under root m and m will get cancelled and we'll have under root mk into L, right? So option, now this is the momentum initially and also after the collision because momentum is conserved, right? So the answer over here is option B, right? Under root mk into L, right? Now you could have also done this using dimensional analysis, right? So you can see that they have messed up with the terms. You can find the dimensional formula for momentum and see which one matches with the dimensional formula for momentum in this option, okay? So that is another lengthy way of doing this, but this is the actual way of doing it, okay? So I think that is all from this topic. Let's move to our next topic. So our next topic is work energy theorem. Okay, not that important topic from BITSAT point of view, but you never know what will be asked. Okay, so one more topic you know, the better you are. Okay, so let's come to this question. Body loses half of its velocity by penetrating in a block 3 centimeters. Okay, so you can imagine the situation over here. You have a bullet. Okay, it penetrates into a block, and after penetrating 3 centimeters, after getting inside 3 centimeters, it will lose half of its velocity, okay, due to the resistive force which is offered by the block, okay. Now how much more will it penetrate before stopping? That is the question. Now if I hadn't mentioned that this question is from work energy theorem, that then you might be puzzled, right, how to go about this question. Now you know, okay, it's using work energy theorem, okay. And how do you use that? First of all, what is work energy theorem? It states that the work done by all the forces is equal to the change in the kinetic energy, okay. So let's consider the first situation over here, which is this, okay. By the way, this is take 2. Anyways, so body loses half of its velocity, yeah. So yeah, so let's take this, okay. So here force, we can write this work as force into displacement, right? And kinetic energy change, we can write it as final kinetic energy minus initial kinetic energy, right? So if you see the displacement in the first case is 3 centimeters, here our main motive is to find the resistive force, okay, and we assume that this resistive force is constant and will apply it in the second case to find D, okay. So that is the idea we are going to use over here, okay. So yeah, so here we have the force, final kinetic energy. If you see, the body loses after 3 centimeters, it will lose half of its velocity, right? So half m v by 2, right? Initial velocity is v, but finally the velocity will become v by 2, okay, only considering this situation over here, okay. And this, if you see, initial velocity is v, so half mv square, this is the initial kinetic energy, right? So you can take half mv square common, so 1/4 minus 1, that is minus 3/4, so half mv square minus 3 by 4. This minus sign just shows that this force is resistive, right? The force and displacement are in opposite direction. 3 cancels with 3 and you have this force. Okay, this force is given to you now. Okay, you know this force now, half mv square by 4, right? So I can write 1 by 8 mv square. Okay, this is the force, resistive force. Okay, and it is constant. Okay, that is the assumption. Okay, it's assumption, but yeah, it's fair assumption. Okay, now let's come to case 2. Here you can see that how much will it penetrate more before stopping. Okay, so again apply work energy theorem. Okay, you write force into displacement. Okay, here you are supposed to find displacement now, right? You know the force and you will also know the change in kinetic energy. Okay, now in the second situation it begins at v by 2 and it goes to 0, right? It stops. Okay, so it begins at v by 2. We have broken this motion in 3 parts. Okay, first it begins, your bullet begins at velocity v, then after going 3 centimeters inside the block it has velocity v by 2, and after some distance d it has velocity from v by 2 to 0. Okay, its velocity becomes 0, it stops. Okay, you are supposed to find this d. Clear? Now if you see in this, now we are considering this motion. We have already considered this. From there we found out force. Okay, now we are considering this motion. Okay, again we can write it is kinetic energy final minus kinetic energy initial, right? And this is minus, right, by the way. So F into D, kinetic energy final, if you see it's 0, right? Because its velocity is 0, finally it stops, so kinetic energy final is 0. Initially it is half mv by 2 the whole square, right? And here you'll have minus 8 mv square into d sub, this something we'll find, and here also you'll have 4 into 2 8 mv square. So if you see this and this will get cancelled and you'll get d as 1 centimeter. Okay, so option C is the correct choice over here. Okay, it will penetrate 1 centimeter more before it comes to rest. Okay, so in total it penetrates a distance of 4 centimeters. Okay, so this is how you solve such type of questions using the work energy theorem. Okay, so let's move to our next topic now. So our topic number 3 is collisions. Again, an important topic from BITSAT point of view. 6 questions in the last 15 years, right? And in that also inelastic collision is the one which is favored more, right? So here you have 2 blocks in this question. One is moving with a velocity of 2 meters per second, its mass is given. Other block is initially at rest, its mass is also given. Okay, now they undergo perfectly inelastic collision. Now you should know what that means, and you are supposed to find the energy loss in this case. Okay, what is the energy loss in this process? Okay, now you'll know that in elastic collisions, okay, in perfectly elastic collisions, okay, perfectly elastic collisions. Okay, I'll not use this, you'll get confused. So in perfectly elastic collisions, the energy is conserved. So initial energy equals the final energy, right? So kinetic energy is conserved, the mechanical energy, kinetic energy basically is conserved in elastic collision. Okay, but in case of inelastic collision, okay, this is a separate thing. In elastic collision, the energy is not conserved, right? There is some loss of energy, and this is something that you are supposed to find. Okay, first of all, what we are going to use, any guesses? Conservation of momentum. I told you in any type of collision the momentum is always conserved, right? So you'll just conserve momentum in this case. So initial momentum equals final momentum, right? So basically what is the final condition? You know that the collision is perfectly inelastic, right? So which means that both of these blocks, this 0.5 kg block and the 1 kg block will move together. Okay, that is what is meant by perfectly inelastic collision. Okay, there is no separation between the two. Okay, once they collide, they stick to each other and move together. Okay, my teacher used to say they fall in love and move together, but come on, right? Love is a very different thing, physics is a different thing. We all know that physics is better than love. Just kidding. Okay, so let's come to this. Now the initial momentum, if you see, it's just due to this block, right? This is initially at rest, so due to this block, mass into velocity, right? And final momentum, if you see, this system will move together with some velocity v dash. Okay, so here, from here we can find that v dash, right? What is the velocity the system is moving with? Okay, so here mass is, if you see both of them, you have to add the masses, right? These two are moving together with velocity v dash. So 0.5 plus 1, 1.5 into v dash, m total into the velocity, right? So this is the initial momentum, this is the final momentum. Let's find what is v dash. V dash, if you see, is 1 by 1.5, 1.5 is 3 by 2, so 1 by 1.5, 2 by 3, or 0.67. Okay, 0.67 is v dash. Okay, so that is our v dash. So we know the final velocity, we know the initial velocity. Okay, can't we find the change in kinetic energy? We can, right? And from there we'll see what is the change, and that change is nothing but the energy lost, right? So due to this collision, this here will have the half mv square, the final and velocity, the final kinetic energy. Here we'll have the initial kinetic energy. The difference between the two will give us the loss in the energy, right? So energy loss is basically the initial kinetic energy, so half m, okay, I'll write it as a formula, v square minus half m. Here m is separate, it's capital M, both the masses together, v dash square, right? So you can take half common, and here you'll have 0.5 into v square, 0.5 into 2 square, which is 4, minus half is taken common, and here you have 1.5, mass is 1.5, and v dash square, v dash is 2 by 3, right? 2 by 3, you square it. Now 1.5 you can write it as 3 by 2, 2 by 3 squared, right? V dash square, so the square, so you can cancel this, this will also get cancelled, so you'll be left with half. Here it is 2, right? 0.5 into 4 is 2, minus 2 by 3. You can take 2 common, and this 2 will cancel throughout. So 1 minus 1/3. 1 minus 1/3 is nothing but 2/3, which is nothing but again 67, right? So 0.67 joules. Option C is the correct choice over here. Okay, so what did we do? We just conserved the momentum, found the velocity of this system which is moving together because it is in perfectly inelastic collision. Okay, we found v dash, we just then we found the final kinetic energy, we found the initial kinetic energy. The difference between the two is nothing but the energy loss, right? So let's move to the next question now. So question number 2 on elastic collision now. Okay, this is a perfectly elastic collision. You can see a mass m moving with a velocity u in the x direction. 3m is initially at rest. Now after collision, the mass m starts to move purely in the y direction. Okay, with the velocity v j cap. Okay, it's in the y direction, and 3m moves in some random direction with velocity v dash. Okay, you are supposed to find the velocity v. Okay, you are supposed to find this velocity v, not v dash, v. Okay, so let's try finding it, and you are supposed to find v in terms of u. Okay, so that is the question. So first of all, we are told that it is an elastic collision. First of all, it is an collision, it is a collision. Okay, so momentum will be conserved, right? So you can write initial momentum equals final momentum. So initially the momentum, if you see, this is at rest, so the initial momentum over here is m into u I cap, right? Okay, and here you can write the final momentum. If you see, it will be m into v j cap. Okay, now momentum is a vector, so I am writing it this way, plus 3m v dash, okay, v dash vectorally, right? So if you see, m will cancel out throughout. Okay, one thing we can do, we can find v dash from here. Okay, I'll tell you why later. Okay, we'll use that in kinetic energy. Okay, you'll see that it is u, so this v dash is nothing but u I cap minus v j cap, right? So this is the value of our v dash. Okay, so this is in vector form. Let's find its magnitude, right? Because in kinetic energy, we just use the magnitude, right? We don't want the velocity, we just want the speed, right? V square, basically focusing on the magnitude, right? So we'll find the magnitude of this thing. Okay, so once you find the magnitude, it is under root, am I missing something over here? Okay, this 3, yes, it will be divided by 3, right? Ui cap minus vj cap divided by 3. Okay, yes. So now let's find the magnitude of this. So square this term divided by 3, yeah, that I will keep over here. Okay, so this square plus this square, right? That is how you find the magnitude in component form. I told you, right? If you have a vector like a x I cap plus a y j cap, where a, these terms are constant, then basically the magnitude of this vector is given as under root of ax square plus ay square. Okay, so u square plus v square, right? So that is how you find it, and here you'll have 3 only. Okay, it's under root 9, so 3. Okay, fine. Now the next thing to do is to equate the initial kinetic energy to final kinetic energy. Remember, this is elastic collision, right? In elastic collision, in space elastic collision, the energy is conserved, right? Kinetic energy is conserved. So you can write initial kinetic energy equals final kinetic energy. Okay, only in case of perfectly elastic collision. Okay, so initial kinetic energy, it's over here, you'll write it as half mu square. Okay, only concerned about the magnitude this time. Okay, kinetic energy is basically a scalar, right? So here, coming over here, you'll see it's half mv square, right? And here plus half 3m into v dash square. This one, so half 3m into v dash square, right? Now v dash square, we can find it from here. We can write it as u square plus v square upon 9, right? U square plus v square upon 9. This is not under root, so it becomes 9. Okay, so here you can cancel m throughout, and you'll be left with, you can also cancel half, so you'll be left with u square is equal to v square plus 3 into v dash square, which is over here u square plus v square divided by 9. So this and this can get cancelled as 3. So u square equals v square plus u square plus v square by 3. Okay, just solve this and you'll have your answer. So this becomes 3u square plus 3, okay, is equal to 3v square plus u square plus v square. Okay, fine. Okay, am I doing a mistake over here? No, let's solve it. So here you'll have 4v square, okay, and here you'll have 2u square, correct? Okay, 4v square and 2u square. Okay, so you are supposed to find v in terms of u, so v square will be given as u square by 2, right? V square will be u square by 2, and v will be nothing but u by under root 2, okay, which is option C. Again, option C, right? So yeah, v is equal to u by under root 2 is the correct choice over here. Okay, so we used momentum conservation and energy conservation because it is a perfectly elastic collision, right? So final question will go to the chain system that we had discussed. Only one question was asked in the past 15 years. Again, that is important. We'll discuss it briefly and let's end the chapter over there. Okay. So our fourth topic, which is the last topic for the day, which is chain. Okay, chain problems, you might have heard of this. Okay, so here we have a chain whose total length is L. The mass of this chain is M. Okay, you have 1/n of the total length hanging. Okay, this is the length which is hanging, 1/n of the total length. Okay, you are asked what will be the work done to pull this hanging part back onto the table. Okay, So basically you are supposed to use that work done is equal to the change in the potential energy. So if you see, this is the initial configuration, right? Finally you want that the entire chain should be on the table, right? So this is the final configuration, right? This is the initial one, this is the final one. What will you do? You'll just find the change in the potential energy in these two configurations, okay? So that is the basic idea over here, and that will be nothing but the work done, right? So you can see that in final case the chain is completely resting on the table, okay? We'll choose that this is our reference level, and this at this level the potential is 0, okay? So our potential energy at this level is 0. So here in the final configuration our potential energy is 0, okay? So here we are supposed to find the change which is final potential energy minus initial potential energy, right? Final is 0, okay? We'll find the initial potential energy using mgh, right? mgh. Now if you see mgh, I'll just write the formula. If you see the hanging length, okay, this is the part of which we are supposed to find the potential energy, okay? So what is the mass of this length? Okay, what is the mass? If you see, the total length is L, for which mass is m, right? For length L by n, won't the mass be m by n? Correct? Yes. So yeah, the basically it is linear, okay? Your chain is linear. So if you divide the length by L, okay, suppose if you make the length half the length is hanging, then the mass hanging will be also half, okay? There is a linear relation between length and mass, okay? So that is the case over here. So our mass which is hanging in this case in initial configuration is m by n, right? G is as it is, okay, we'll keep G as it is, okay, that is acceleration due to gravity. And what is the h? Okay, if you see what is the h over here, the chain is spread throughout, right? It's not that mass is concentrated at this point, okay? Actually it is concentrated at the center of gravity, okay, at the center of mass, okay? So where is the center of mass over here? It's at half the length, okay? The length, hanging length is L by n, okay? What will be the half of this? L by 2n, right? You just divide this by half, and here you can consider that this entire mass is concentrated, okay? And basically instead of imagining this as a spring, you can just imagine this as a ball which is hanging over here and with mass this, okay? You just have to bring that ball back to the table, okay? So here you can see that height will be this height, okay, from the center of mass to the table, okay? Now it's in the negative direction, so I'll write minus okay, even if you don't consider the sign, it's okay, but yeah, it's in the downward direction, so it's minus h. Now what is h? It is half of this length, right? So it is minus L by 2n, right? So here you'll get mgl by 2n square minus, right? This is the initial potential energy. Substitute it over here and you'll have your answer as mgl upon 2n square, right? And that is nothing but the work done. Okay, yeah, mgl by 2n square. Okay, so this is how you do the chain problems. You just consider the mass of that spring using the linear relationship, and you just find the change in the potential energy in the two configurations, okay? And here you consider that the mass is concentrated at the center of mass, okay? This works because your potential energy is a function of h, okay? It's linearly dependent on h. Otherwise for some other power it would not be, okay? But anyways, it will work in this case because there is a linear relationship between the two, okay? So yeah, that's pretty much it for today's class. I hope you enjoyed it. By the way, thank you for 200 subscribers, really keeps me going. I'll see you soon in the next video. Do check out the previous year questions of BITSAT from this chapter. Click over here, okay, and click here to subscribe. I need more of those. Anyways, bye, and I'll see you soon in the next one. Till then, keep enjoying physics.